Hello everyone, my name is Ni. I'm from the Institute of Civil Engineering at Technical University of Berlin in Germany. And now I'll give you the short presentation with this topic on resistance of re-stiffened welded beams subject to the axial compression. Actually, I'm here to take this presentation for my colleague Dr. Jaeger-Canas, and he working in this company and now is on vacation, so he's not here today. And now it's the content, and at first it's the introduction, and then we made a lot of numerical study as parameter study, numerical simulation as a parameter study, and after that, based on the numerical results, we proposed a simplified approach which can use the hand calculation for re-stiffener shear structure, and last is the conclusion. We know that the re-stiffener shear structure, I mean the tanks and the silos, are widely used in many industry fields. And here in this slide, you can find some real tanks structure with re-stiffener. Here you can see the re-stiffener. Here also you can find some re-stiffener. And uni stiffener can increase the stability of the thin shears to make a high material efficiency, and this kind of stiffener cannot only just prevent the buck buckling due to the wind, but also reduce the risk of the stability failure of the shear structure caused by axial compression. And according to the private research result with very close spaced stiffener, such as with a distance about one bucking half length, it has a huge strength enhancement compared to the unstiffened shells. And sometimes with a heavy stiffener, a real buckling load can reach about 1900 of the classical critical load. And so using a re-stiffener can really reduce the material cost. And here in these two pictures, you can find the buckling shape of unstiffened and stiffened shell. Here, without a re-stiffener, we can find the global buckling. And here, this is silo. Here, we find some uh, re-stiffener, and here just local buckling. I think because here the re-stiffener can reduce the uh, extension of the local buckling to global buckling. And in this study, we made some parameter study for the re-stiffener shear structure. Usually, we can use the ring parameter to describe the stiffness of the stiffness of the re-stiffener. And here from this is the equation we can find the ring parameter is proportional to the cross-section of re-stiffness, and is the inversely proportional to the stiffener um, spacing, and the T, the shear thickness. So theoretically, a larger ring parameter has a large or more re-stiffener. And according to the previous numerical and experimental study, we find here a shear with a larger ring parameter has a larger, had more um, buckling berry capacity. So for the sorry, for the parameter study, we used the finite element software sophistic with a shear element, and we assumed that all material are S355 steel without a hardening, and the reference thickness is 1 millimeter, and the height to radius ratio was defined as 2. But if with this height it can only put less than 3 re-stiffener, then we will increase the shear height, and to reduce the calculation time, we modeled only 1/4 of the cylindrical shell, and according to the mesh convergence study, we used different mesh size in two directions. Here, this is two directions, different mesh size with this is value. And all calculations are used geometric and material nonlinear analysis with the welded type A infection. And in total, we made more than 3,000 numerical simulation, and we considered a lot of a combination of the different parameters. For example, here we defined the two different ring parameter KST, and then we changed the stiffness spacing again with different value. So we analyze the influence of each parameter, and we find this is very complicated issue. So we developed a simplified design method for practice according to the numerical parameter study. And at first we define that uh, this is a simplified model can only apply to the structure with the ring parameter small or equal to 1, and the RT ratio needs to be less than 10,000. Actually, this value is relatively large compared to the current code, which is just 5,000. I think 5,000. I think, and at last, the wrist stiffness spacing need to be larger than 2 times the half-wave length of buckling. We know that a small stiffness spacing can further improve the barrier capacity of the shear structure, but in real shear structure, we don't use it such a small specimen of wrist stiffness. So for this approach, at the first step, we need to determine the equivalent infection amplitude because the ring stiffness reduces the infection sensitivity. So we use the equivalent value to modify this kind of influence. And then we need to calculate the elastic infection reduction factor. Here we have three different equations for different stiffness spacing. Here is the 2 times the half buckling wavelength. Here's 3 times, and here the space is the infinity. This means without wrist stiffness. And then, according to the real stiffness spacing of the design structure, we can use the linear interpolation to calculate the real uh, elastic reduction factor alpha. And for wrist stiffness, actually we need to consider the influence of geometric infection caused by the welding process. And in our simplified approach, the calculated elastic reduction factor will be reduced based on some parameter. Here the ABC from this is the table, and this is the value is obtained from the parameter starting of the welding parameter starting for the welding infection position. And after that, uh, the plastic range factor and the buckling curve exponent can be calculated with this is to modify the equation, and this is equation, or this is the parameter of the equation. For example, here is from is using the curve fitting approach based on the numerical result. And then, according to the current design code, we can calculate the corresponding slenderness, and the last step is calculate the buckling reduction factor, and just like we already used in our design, according to the Euro code. And to verify the accurate, accuracy of the simplified model, we compared the numerical result and the result from developed approach. Here, this is y-axis means the ratio of the result from finite element method and the calculate value. And here the x-axis is the relative slenderness, and here this left side is with the stiffness spacing KST 0.4, and here's 1.0. And here we can find from these both diagrams when the space AST larger than 2.0, and the most ratio value is larger than 0.9. So we think this is the design approach is safe. And from this diagram, we can find in the largest slenderness, relatively large slenderness position, the most result is not very conservative. So this is maybe due to the consideration of all infections case. And if we consider more parameter combination, the result has a larger scale. And I think this is just because the simplification. Because with a simple equation, it's very difficult accurately to describe all numerical simulation results, especially as all considered parameters depend on nonlinear from each other. So this simplified approach is not perfect, but we think it's suitable for the practical um, restricted shear structure, and it's very easy to use. It can calculate with hand. So as a conclusion, we can say we made the primary starting for the restricted welded shells under axial compression with numerical method, and we also discussed the influence of the welding position, ring parameter, stiffness spacing on the variable capacity, and we also developed a simplified design method with a hand calculation for re-stiffened shells. So thank you very much for your attention.